Hey teams, I'm Coach John Burnett, and in this video, I'm letting two of our control team members, Devon and Adrian, walk you through how to get your robot up and running from the programming side of things. They're going to help you use LabVIEW to go from a blank slate all the way to a driving robot. Before we begin, be sure to like and subscribe so you don't miss another episode. And then leave a comment below with your team name and number so we know who's tuning in. Now, there are several languages supported by FIRST to program your robot. These include C++, Java, and Python, but we are going to focus on the language we use often, which is LabVIEW. You will find many websites offering the incredible intricacies of what LabVIEW can do, but here we are just trying to get your robot up and running. And for those of you watching who are LabVIEW experts, just know that we are likely going to show some inefficiencies or improper use of some functions. Leave those comments below to help other teams, but we are here to help get robots up and running. So let's get programming with LabVIEW, because this is how we robot.
Hi everyone, this is Devon, and I'm going to walk you through the very beginning of the program. Okay, first we're going to assume you've installed both the latest version of LabVIEW as well as the FRC Update Suite. You have to install both for the program to work with your robot, and note that whatever competition year it is, LabVIEW will always be one behind. So if you're watching this during the 2022 competition season, you'll be losing LabVIEW 2021. If you're using any Falcon 500 motors, you will also need to install the Phoenix Turner software from the Crossroads Electronics. This is a good idea anyway for other troubleshooting, so we've linked that description below. Okay, next we want to open up LabVIEW and choose to start a new FRC Robo-Rio project. This will prompt three things from you. First, at the top you need to make a name for this project. We will call this one Simple Drive Code for the purpose of the video. You can name yours however you would like, but try and be descriptive. Just like in CAD, naming a project something like Pineapple will lead to headaches in communication later down the season. Second up is your team number. We will enter in 4327 for our team, but please adjust this for your own. And lastly, you have to determine the style of drive. For this example, we would choose arcade style. In this drive style, the left joystick on a gamepad operates the forward and backward power, and the right joystick will adjust the direction left and right, much like you would find in a racing video game. Press finish and LabVIEW will then auto-populate a program just for you. Now the program is done processing the setup, you will see a relatively small window on your screen. Press the plus sign next to team code, and that folder will then open up a lot of virtual instruments, or VIs. These basically mean small, separate segments of the overall program that will work together to become instructions for your robot. We are really only interested in three for the sake of this video: begin.vi, Teleop, and finish.vi. In the competition, we are also interested in autonomous independent.vi for the autom portion of the match, and sometimes the periodic functions.vi for some more fancier programming. Otherwise, please leave things alone. Okay, so next we want to open up begin.vi by double-clicking on the name. A gray box pops up with nothing besides something called error in and error out. But this is the program. So next up, you will have to press Ctrl and E at the same time to pop up the actual programming. Now this may not look like your traditional language lines of code, but this is what's known as a visual block language. The logic and processing is all still here, but there is a visual graphic user interface to help you interact. Notice there are some items already on the screen as generated when we first started the program. Begin.vi is where we tell the computer all of the motors that we are going to use, what PWM slots that they are plugged into, and what we're going to call them for the rest of the program. First sets up our drive motors as left and right motors, which means anywhere else in the program where we want to do anything with these specific motors plugged into PWM slots 0 and 1, we need to call them exactly with the correct capitalization and spacing. Let me show you real quick what I mean. We are going to add a new motor to the program. To do so, we are going to right-click in the white space to pull up the overall programming menu. Get to the bottom where the WPI robotics library is located. We are going to click on the pin so this stickies to the screen instead of disappearing every time we click on something. Now click on Actuators, Motor Control, and Open. This is an orange box that we are going to click into with the white space on our screen. Now when you move your mouse cursor over the box, there are many tiny dots that show up all around it. These dots have their own function, but the first thing we want to do is tell the program what PWM slot to look for this motor in. To do that, move over the dark blue dot called PWM channel on the left side, right-click, and choose Create, and then Constant. This pops up a blue box with the PWM 0 inside and a line connecting to the orange open box. Go ahead and left-click on the box to open the drop menu and then change the number inside to 2. This tells the robot to look for this motor in the PWM slot 2. Next, we need to give this motor a name. To do that, we are going to go back to the sticky window and choose the arrow going in. Same idea as before. We see many dots around the outside, but this time we want the pink dot called refnum name. Right-click and then Create. Constant. Now we want to call this motor something. Be sure to come up with a consistent naming structure with your team to avoid misnaming this motor later on. Our robot once spent the whole match doing nothing because we accidentally put a space before the name of the motors. Whoops. Let's call this motor Climber. Supposing this would be our climbing motor, let's now connect the open box arrow in box so these two know to talk to each other in defining our motor. This is done by left-clicking on the open box in the upper right corner to the upper left corner of the arrow in box. Then again, from the bottom right corner of the open box to the bottom left corner of the arrow in the box. Finally, we need to be sure we have the correct motor controller selected in the open box. There are many options here, so be sure to know what motor or speed controllers you are using on the robot and choose the corresponding name here. We like the Victor SP controller, so we would choose that. Just to show you, we could also open up the solenoids here with pneumatics. We could open up and define encoders for motor control. We could also open up servos. In this video, we are getting up to speed with basics, but all of these are done in similar ways to what we just showed you. Let's now move on to the Teleop, where we will now tell the programming what to do with these motors in a match. And I'm going to turn it over to my fellow programmer, Adrian, to help you out with that.
Thanks, Devon. This is Adrian, and I will walk you through the Teleop phase of programming. Come back to a small window where we started, and this time double-click on teleop.vi. Another gray window will pop up, and again we will have to press Ctrl-E to open the block diagrams for programming. We will again see the left and right motors referenced here, and they are already connected with orange lines. That is all well and good, so we will leave it alone. Where we want to focus is these beige boxes that have the orange and then green lines coming out. These are arrays to define what buttons or axes are being used to activate the motors. By default, these start at 0 and progress with integers. The issue here is that up and down on the left joystick of the controller axis is 1, and then the left and right axis for the right joystick is axis 4. We know this from the FRC driver station. We can look at the USB tab and see in real time what axes correspond to which physical part of the controller. This also goes for the buttons, which begin at the top with button 0. So to tell which program which axes we want, we move our mouse cursor over the array and then to the left side of the beige box. The little blue dots appear again, and we are going to right-click and choose Create Constant. This will pop up a blue box like we did before with the PWM slot, but this is to define the axis to correspond with the action as shown by the orange line coming out the other side. So let's choose to put a 1 in the first box to correspond to the x-axis value, and then repeat this action and put a 4 in the bottom box to correspond with the y-axis value as labeled on the arcade drive box. Note that you should need more actions or axes. You can click and drag down the beige box to add more nodules there. Now that the drive motors are set, let's get back to that climbing motor. To do that, we need to recall the motor. Head back to that stickied window with all of the FIRST Robotics Competition specific options, and again go to the motors window, and this time we want the arrow coming out. Move the mouse cursor over the box and right-click on the pink dot to create constant. Here we need to put the name exactly as it was defined back in the begin.vi. We use all lowercase to write climber, so we will do that again here. Next, we need from the motors window set output box. Before we actually set the output, Be sure to connect the tops and bottoms of the arrow out and the set output boxes so they know to talk to each other, just like we did back in the begin.vi. To set the output, we need to think about whether we want to use the axis or a button. Using an axis gives us variable control over the speed of the motor, while using a button generally gives us one set value. The difference here in the programming is whether you connect the output to the orange line beige box or the green line beige box. Orange lines are for axes like we have with the drive motors, and then the green line is for buttons. For this video, we are going to connect to a button. Note that the program does not already give us an array attached to the button line for our gamepad. To solve this, we will go to our secret technique of copy and paste. Simply left-click on the desired item, in this case the index array, and then press Ctrl-C and Ctrl-V. Another index array pops up and we will move that into the place where we want it. To make this read the buttons, we will left-click on the orange dot in the upper left-hand corner and then connect to the green line. Anywhere on the green line will do. Now you have a button array. Unlike an axis, buttons are Boolean and just read on or off. So we need to tell the program what to do if the button is pressed, as well to do if the button is not pressed. To do that, we are going to use a true-false gate. This is found by right-clicking in the white space and going to the comparison window of the pop-up. Click on the true-false gate that looks like a triangle. Put this somewhere near the button beige box for now. Now connect by left-clicking the middle of the left side of the true-false gate to the top element or dot of the beige box array for the buttons. Remember, this is the one with the green lines going in and out. Now this gate is associated with this button. True if the button is pressed and false if not. Even though this node is set to 0 by default, I want to be sure of this, and so we will right-click on the blue dot of the left of the beige box and create constant to be sure the button value is 0. Next, we need to tell the program what power to set the motor to when the button is pressed. Do this by right-clicking on the upper left side of the true-false gate and create constant. If you want 100% power, then enter 1. Repeat for the false case at the bottom left corner and choose 0. Finally, connect by left-clicking the right side of the true-false gate to the set output box on its left side. Now whenever button 0 is pressed, the motor will receive 100% power, and whenever it is not pressed, the motor will receive no power. Great! Now the program knows there is a motor called Climber connected to PWM slot 2 on a Victor SP controller and what button gives the motor power. This process is very similar for solenoids, but know that you cannot put numbers down in their cases as the pressure is either on or off from the programming. You will have to create a constant, and the 4 options are on, off, forward, and reverse. Using encoders and servos is more complicated, but resources are available and examples are linked down in the description below. Now back to Devon for the finishing touches.
Thanks, Adrian. Finally, we've reached finish.vi. Double-click on this from the small original window and see a gray box pop up. Go ahead and press Ctrl-E so the programming window becomes visible. In this VI, we really do not understand what happens, but we know we are supposed to do the following for all joysticks, motors, solenoids, encoders, solvers, and etc. We are going to get the arrow out box from the actuator window that we stacked. We are going to create a constant for the name of the motor we defined back in begin.vi. In this case, we create a climber. We are then inside the case structure seen in here, going to get the closed box from the actuator window. And lastly, we connect the tops and bottoms together so they talk to each other. What happens if we do not do this? I really don't know, and I do not want to find out the hard way. Now the programming is all set. The last thing to do is to go back to the original small window. At the very bottom, we see FRC Robot Boot Up Deployment. Go ahead and right-click on this and choose Build. You also want to save your program at this point so you can avoid all crying when the computer crashes and all your work is lost. LabVIEW does not automatically save like Google Docs or something, so the save icon is always going to be your friend. After the program is done building, we will then connect to the robot either wirelessly or via USB cable between the computer and the RoboRio. Quick note while the program is building. You will find the FRC Update Suite, a RoboRio imaging tool. Be sure to use this tool to give your RoboRio the most up-to-date firmware and image before deploying any code. This needs to be done via USB cable to avoid any issues. The last step is to again right-click on the deployment and choose Run as Startup. Do not click Deploy. Choosing Running as Startup blocks in your program even when the robot gets turned off or unplugged later. If you choose Deploy, then if the robot loses power, the new program is wiped and the robot runs on whatever the last Run as Startup program was. And there you have it, a robot program with drive motors and bonus climber motor for you to tinker with around later. We did not get to the autonomous programming portion in this video. Look for that bonus video on a later date. For references of examples of LabVIEW code in various scenarios, we recommend the great people of Team FRC Team 358 who helped us out in a jam from time after time. If you're having trouble, there are always teams and people out there willing to help. Thanks for watching and being with us here today. Remember to leave a comment with your team name and number so we know what robots to cheer for this season. And as always, subscribe to this channel to keep finding out more on This Is How We Robot.